Good afternoon, everyone. Myself, Milind Kansara, Assistant Professor in Electrical Engineering Department. Today we have Professor Nikunj Khatri, RNGPIT College, and Kaushal sir from the VNSGU. I request Professor Nikunj Khatri sir to introduce Kaushal sir. Nikunj sir.
Thank you, Milind sir. It's my privilege to introduce Dr. Kaushal sir. He is an assistant professor in Maths department at VNSGU Surat. He holds huge teaching experience of 14 years. His research experience is of 8 years. He has published 8 national and 30 international papers in various reputed journals. And his research area is fluid flow in porous media, Lattice-Boltzmann method, modeling and simulation, and numerical methods. Till date, 7 students have completed MPhil under his careful supervision, and he has supervised 1 PhD student. Many other students are working under his guidance at present. He is always brimming with energy, and you will soon experience this power in his presentation today. So now, I hand over the control to Kaushal sir. Thank you.
Okay. Kaushal sir, it's up to
you. Thank you, Nikunj sir. So today we are just going with the discuss the concept and application of linear algebra. So in this particular session, we are not discussing about the hardcore definition of linear algebra, but how the linear algebra can be visualized and how the common people can be understand the linear algebra. That is our goal, our aim to today's lecture. So, as just making this particular presentation, I visit so many sites to find out how the linear algebra can be worked. So, at beginning, I just searched the definition of linear algebra, and the definition that come from the Wikipedia is a linear algebra is a branch of mathematics concerning a vector space and linear mapping between such spaces. So now, whenever we're discussing this particular definition, there are so many words that are not understood by the normal people, those who are not in mathematics. So there are certain words are vector space, linear mapping, and so on. So it is a very confusing definition. So can we dilute this definition to reach to the common people or common students, those who are eager to learn linear algebra? So we are simplified our definition. The linear algebra is a study of system of linear equations. So it is very easy to understand. It's a system of linear equations. But now, again, we can just go to the what is equations and what is functions. So first of all, we are just going with the what is the difference between function and equations. We understand the difference between function and equation that can helpful to get the better understanding of linear algebra. So the equation, an equation is a two expression with an equal sign in between. It is like y equal to 2x plus 1. So there is left hand side, there is a y, right hand side it is 2x plus 1, and in between there is equal to sign. This is the equation. And a function is an expression, a formula, means this considered as a relationship between the variables. One input values gives one output value or values. Means that can be considered as the same thing. So 2x plus 1 is an expression that could be named as fx. So it's an expression, and the above in equations we have what the two expression. So always we have two different domain of equation and function. So there is certain domain in which the only equations can satisfy, certain domain that consider as only functions can specify, and there are certain common domain between equation and function. So we just go with the example of equations. So let's x square plus y square equal to 1. So this is called equation. This is not a function. Whenever we go with the function fx equal to mod x, or fx is equal to, there is a piecewise continuous function. It is 1 where x greater than 1, greater or equal to 1, and minus 1 where x less than 1, less than 1. Sorry, there is a typical mistake. And there are certain things that are considered as an equation and function both. So y is equal to 4x minus 1, that we consider as it is a function as well as the equation. So now we can just further going towards the example of the function and equation. So we are just going with x plus y equal to 1, that gives y equal to x plus 1. It's a function. So we can just graph it, and it is considered as a straight line. Now second one, we just go with x square plus y square equal to 1, that gives y square equal to 1 minus x square, that gives y is equal to plus or minus under root 1 minus x square. We consider this is not a function, because whenever we consider y equal to 0, x has a two different value, x equal to 1 and x equal to minus 1. So now whenever we sketch the graph of that, it is x square plus y square equal to 1, that's a circle. There is two other example of that we have considered here. So this is x square plus y equal to 1 implies y equal to x square plus 1. So it is a function. And whenever we consider x plus y square equal to 1, that implies y square equal to 1 minus x. That is nothing but y equal to plus or minus under root 1 minus x. This is not a function. So here we consider that. So the third blue one is nothing but one kind of parabola over there, and green one is also a parabola. One is a function, other is not a function. How you can easily identify whether the given equation is a function or not? So here we have one here we have one line test. Actually, this is called horizontal line test. When it passes through the graph and it is teaches to two different point of the graph, then definitely it is not a function. And if it touches only one point on a graph, then we can say that it is a equation. Sorry, it is a function. So linear equation. So any patterns of a number that is increasing or decreasing by a same amount over step, then it is called a linear equation. Definitely, whenever we have a linear equation, it has two things. One, it is a beginning point and how it can move. So it is only defined as two things. One is begins, how it begins, where it moves. So the simple form of this one is nothing but y equal to mx plus b. For moves, it becomes m. For beginning, it gives b. So here we have two different examples how the linear equation comes from the real life. So here we are considering the two different examples. We are just going with the first example, that is a linear equation. Suppose I buy a car, that's an old car, which is of 20,000 kilometers. And I used to travel 12,000 kilometers per year on an average. So I have to predict that after X years of purchasing of an old car, what will be the kilometer it would be traveled. So definitely the equation is nothing but y is equal to 12,000 multiplied by x plus 27,000. So generally thing is it begins whenever I purchase a car, it already traveled 27,000 kilometers. And every year I used to travel 12,000 kilometers. So this equation becomes y is equal to 12,000x plus 27,000. Similarly, whenever we have to purchase the house, the cost of house is nothing but 2,700 rupees per square feet. So now my cost of house is nothing but y equal to 2,700 multiplied by x. There is no initial forms. There is no beginning. So no beginning means there is a 0. So here we are, if there is no b, consider as 0. So for simplification, simplified form of the linear or uniform form is nothing but the straight line. When it becomes curve, then it is non-linear. So next is nothing but how to solve an equations. So we are just going with what is equation and how it can be formed. So general form of linear equation is nothing but a1x1 plus a2x2 plus an(xn) equal to b1. So we are just going with the example of that. Minus x plus pi y minus root 2z equal to 0.07. Here we just comparing with the original equation, general form of equation. So a1 equal to 1, a2 equal to pi, a3 equal to root 2, and b1 equal to 0.07. Similarly, we have equations actually in form of 2x minus y plus 6 equal to 13 minus 4x. So we can convert into the what general form by adding and subtracting certain things, and ultimately we get a new equations. This is called 6x minus y equal to 7. Here a1 equal to 6, a2 equal to minus 1, and b1 equal to 7. Similarly, next example is nothing but root x plus 1 upon y is equal to wz. Here wz minus 10. Here that can be simplified as a x raised to 1 by 2 plus y raised to minus 1 minus wz equal to 4. Let's here we consider as a 4 variable x, y, w and z. But the power of x is 1 by 2, power of y is minus 1, w and z are in multiplicative factors. So whenever the power is more than apart from 1, we consider that any equation that has a variable has a power apart from 1 that consider as a nonlinear equations. So now we are easily find out that we can go with the linear equation, how we identify the linear equation and nonlinear equation. Now a solution, ultimately our focus is towards what is the solution of the equation. A solution to the equation is a value for which variable that makes the what equation true. Means we have to find out the value of x1, x2 up to xn so that the whole equation from left hand side value and right hand side value becomes same. So for example, here we are just going with x equal to 3, y equal to 4 and z equal to minus 5 is the solution of an equation x minus 4y minus 5z equal to 7. Ultimately, we just substitute the value of x, y and z in equation. We have satisfied what right hand side and left hand side both are same values. So now whenever we go with the system of equation, the system of linear equation is a collection of one or more linear equation involving the same variables. So now for example, 2x minus y plus 1.5z equal to 8, x minus 4z equal to 7. Now a solution to a system of linear equation is a value for each variable that makes each equation true. So solution are often written as a what order tuple as x1, x2 up to xn, where x1 is a value of for x, x2 is a value of for y, x3 is the value for z, and so on. So now we just check whether minus 3, minus 8 and 4 is a solution of this system of equation or not. So just we are taking the first equation and we substitute the value. So when it is satisfied, then we can say that this particular set of values can satisfy the first equation. So we just going with 8 equal to 8 means this set of values satisfy the first equation, that's triplets. X minus 4z equal to minus 7 satisfied by minus 3 minus 8 4 means this triplets may or may not satisfy these equations. Let's we check. This is nothing but minus 19 equal to minus 7. This is not satisfied. Means this triplets never satisfy this system of equation. So let's just check whether 5, 6.5 and 3 is a solution to this system of equation. You just check whether it is satisfied or not. That is a task for yours. Okay, now whenever we have a solution, there are 3 different kind of solutions that we get. Either the system has one solution, either the system has many solutions, or either the system has no solution. So we just taking the system of 3x plus y equal to 17 and 4x minus y is equal to 18. So we cancel out y and we have 7x equal to 35 and x equal to 5. Now we substitute the value x equal to 5 in any of the above equation, we get y equal to 2. So this gives that it has a x equal to 5 and y equal to 2. This is a consistent, means 2 variables, two unknowns we have x and y. We get the unique value of both the variables. That's why the system is consistent and they are independent. The below graph says that it can touches the only single point. Now whenever we just go with the many solution, the example is nothing but 2x plus 4y is equal to 8. That is nothing but x plus 2y is equal to 4. just we are just cancelling the, okay, just we multiply the second equation by -2, that is nothing but 2x plus 4y equal to 8, and -2x minus 4y equal to -8. So it cancels both the variables x and y, means 0x plus 0y equal to 0. This equation is universally satisfied. So we can say that for x different from y, means we can take any value of x and any value of y, we have a consistent solution. But it is dependent. It is depends on x and y both, means one variable keep constant, other variables can vary. So this is the way we can get the solution, and we get the many solution. So here we have for these two equations we get a straight line. There is only single line is there. So whenever we have a single line, then definitely it gives a many solution. The certain example that are related with the no solution, 3x plus 2y equal to 5 and 6x plus 4y equal to 8. So whenever we just subtract it, multiply first equation by 2 and subtract it, we can get 0x plus 0y equal to 2. So this is for x or y, may take 0, it gives value 2. So how it possible? This is inconsistent equation, and whenever we make a plot of that, it is a two separate line, parallel line we get. So whenever we, from the graph, we can easily identify whether it has a solution, it has a many solution, and whether it is a no solution. So when it intersects at a single point that has a one solution, there is only one line, a dependent forms. So that's why we consider as a many solution, and the line never touches to each other. Then we can say that it has a no solution. So we can easily find out the given system of linear equation. We can say that it has a solution, no solution, it is a one solution, unique solution, or it has a many solution. How we can find out that? So for that, we first go to the fundamental element of linear algebra. So here the fundamental element of linear algebra is a vector, and there are different branches in which the vector can be identified with the different names, different characteristics actually. So here we have three different branches in our system. There is a physics, computer science, and mathematics. For all where we can get the vector in a different manners. So we just test how the vector can be identified in a physics. So we are just going with there is an arrow pointing in a space. This is considered as a vector in physics. So it has a length and direction of pointing. So it has a length actually. We can find out the length of that. It has a direction we consider as a physics. And the third one is a very important thing. It moves in the space, and it is the same vector. If we are making the vector here or there, no problem. It's a vector. Fine. So it does not make any sense. Their characteristic is same everywhere. It changes the position. The characteristic is not different. So it is a two-dimensional vector or three-dimensional vector. There might be, it is a example of two-dimension vectors, and it is an example of three-dimension vector. Now, whenever we go with the computer science, it is a list of number. So whenever the thing is listed, we consider as it's a vector. Second thing is nothing but order list of number, means 2, 1, 0, 0, minus 3. 2.3 is minus 7.1, 1.0. It's a sets of number, and it is in order. So we can say that it is a vector in a computer science base. So we just going with the whenever we have a house, and it is of 2,600 square feet, and its price is nothing but $3 lakh. So how it can be represented? In the form of vector. So this can be defined as 2,600 square feet with the price $3 lakh. So that cannot be, we are altering that values is different, their vector is different. So the order is important, and it is of two dimension because we have two things to represent that vectors. So that's why it is of two dimension. So now the third one is nothing but vector in mathematics. So at now we are just going with it is an arrow pointing somewhere. It has a length, and it can be represented as V bar, but which has a characteristic of physics and computer science both. So it is of 3 minus 5. That has a number that can be given a magnitude and direction both. So now we have a W, that is another vector which might be considered as 2, 1. Now whenever we have to make mathematics, we make a use of operators. So we are just going with the operators, V bar plus W bar. So this can be nothing but the addition of two vectors. So 3 minus 5 and 2 1. With the addition, we get it is 3 plus 2 minus 5 plus 1, and it gives a 5 minus 4. So here the addition, multiplication, subtraction, division are there in that particular vector, and that is related with the mathematics. Certain vector is that can be scaled, actually scaled with the 2. This is 2v, that can be defined as 3 minus 5, that gives 2, 3 minus 5, that gives 6 minus 10. So that's a scaling factor is there. Means the vector is it has a fundamental operators. It is a vector addition and scalar multiplication. So in mathematics, the vector has a what? The vector addition and scalar multiplication with the two fundamental operators. So now, so this is actually video that I taken from the 3 blue, 1 brown forms. So this is a vector actually. This vector is nothing but minus 2, 3. So it has a minus 2 in x direction and 3 is in y direction. And the resultant forms is nothing but the 2 minus 3. So like this is minus 2 direction in x direction, and 3, that is a parallel to y axis, and it gives the first vector minus 2, 3. Whenever we just go with the second one, 1, 2, it's this one, 2 minus 1, this one, and 4, 0, this means this one. Only the difference in mathematics and physics is only be there. Always in mathematics, vectors start from the origin, whereas in physics, vectors start from anywhere. So that's the definition. That's the difference between the vector in mathematics and vector in physics. So every point in a space has a unique representation as a vector. So whenever we collect any point on the space, here, whenever you can take any point in the space, it has a the unique representation with the order pair of numbers. So whenever we just go with the 3 dimension, so it is one additional,
add a third axis
called
the z-axis.
One additional axis is there, that's the z-axis. Now whenever we make the we have to travel in x direction, we have to travel in y direction, we have to travel in z direction. That gives the triplet numbers. It is nothing but we are traveling 2 things, 2 unit in x direction, 1 unit in y direction, and 3 unit in z direction. We get this vector. Now the solution of system of equation, we have a vector. Now again we back to the solution of the system of equation. So this is a system actually. Now we have to go through a certain methods of that. One is a row method, other is column method, third one is a matrix method, eigenvalues method, Crammer's rule, row equivalent form, reduced row equivalent form. So we just begin with the row method. So how we can? So this is a first and second. There are 2 equations, and this equation is called equation of line. So whenever we have this 2 means certain sets of equation, and we use the row method, we must go through line by line. So we just make we just draw the line of 2x minus y equal to 0, and second thing we draw the line of minus x plus 2y equal to 3. So this is the graph of that. So green one is nothing but 2x minus y equal to 0, and the purple is nothing but blue is nothing but minus x plus 2y is equal to 3. Now the solution of this nothing but the point of intersection gives the solution. Means here this particular point gives the solution of this system of equations. So it just in x is equal to 1 and y equal to 2, that gives the solution of these equations. Now by column method, so here there's a system of equations, same set of equations we have, the converse system into the column form. So that gives 2 minus 1. Here we are just go with the column wise. 2 and minus 1 is a coefficient of x. Minus 1, 2 is a coefficient of y, that is equal to 0, 3. Now our target is to what? To which linear combinations 2 minus 1 and minus 1, 2 produce 0, 3. So we just go with this one. So this is a first vector, 2 minus 1, it's the orange one. And the second one is nothing but minus 1, 2. So this one. Now we just shifted this blue to the orange. Now we have to target our target is nothing but 0, 3. So we just add or stretch this vector in such a way we can get the vector, we can get the resultant vector at 0, 3. So this is nothing but we trace a vector blue in 2, means multiple of 2, means scale it 2, we can get what? The resultant. So definitely the orange one we get 1 and blue one we get 2, and we approaches to the what? 0, 3. So definitely this is gives the what? The solution of this combination gives the what? The solution of the system. A matrix method, everyone knows that we have 2x minus y equal to 0, minus x plus 2y equal to 3. So this a equal to 2 minus 1, minus 1 2, and b is equal to 0 3. So ax equal to b, we have x equal to inverse of a multiplied by b, and that's why x is equal to 1 and 2. So this is a simple matrix method that can be we can get the output of the what? Resultant vectors. The next thing is nothing but this is the eigenvalue and eigenvector. So whenever we just solve this using the eigenvalue and eigenvector, before we just identify how we can say that it is eigenvalue and eigenvector. What is eigenvalue and eigenvector? That is much more important. So here A is a matrix and X is a vector. So A can be defined as 1 by 4, 3 by 4, 1 and 1 by 2. This particular videos that I capture from the MATLAB, it's called Eigenshow. And here there are different value of x and y. We can get the different resultant vector of what? Ax. So here we have x. X is a vector. X is a vector that may be consider as any value of that, and resultant value of here we can get as ax. Now we change the value of x. We change the value of x, and we can get the what? Different resultant from what? Ax. So now, fine. Here we just change the value of x. Definitely the resultant can be can be get in the form of ax. Now this all value of x is not eigenvalues or not eigenvectors. So just we are just going it. Oh, just we are miss out. Whenever it is a coplanar, actually ax and ax, this gives the eigenvalue of that. Let's we just go ahead and find out. Okay, sorry. Okay, so this is what the collinear are there. This is x and ax value, both are same actually. It has a same direction, or it might be opposite direction, but it has the same direction. So this particular vector is considered as a what? Eigenvector. No other vector is eigenvector, but this vector, this considered as a what? Eigenvector, and the scaling factor is called eigenvalue. So let's we just go with the extended form of that. So again, there is another form is nothing but it can be again. Okay, so for this point, it's again a collinear actually. That is in opposite direction, but still it is a collinear. Definitely we can say that this is again an eigenvector. Okay, and the scaling factor is called eigenvalue. So this is the way we can identify eigenvalue and eigenvector of the system. So by the eigenvalue method, we can get the solution of this system. So here A is equal to this matrix 2 minus 1 minus 1 2, B is 0 3. We can just go with characteristic roots of that particular values. So A minus lambda equal to 0. That gives 2 minus 1 minus 1 2, that is minus lambda 1 0 0 1. That implies 2 minus lambda minus 1 minus 1 2 minus lambda equal to 0. The characteristic polynomial is nothing but lambda square minus 4 lambda plus 3 equal to 0, which gives the lambda equal to 3 and lambda equal to 1. For lambda equal to 3, we get the resultant matrix is nothing but 1 1 0 0. So for that, it is what? 1 1 0 0. So this gives the eigenvector. It is not a matrix. So we are just going with resultant matrix with the vector v1 and v2 equal to 0. So that gives, here we have only one equation, so keeping one variable constant, consider as a constant, so assuming as a constant, so v2 equal to t, so it gives v1 equal to minus t. So definitely we get a system is nothing but -1 and 1. So for lambda equal to 1, similarly we can just go with lambda equal to 1, we get eigenvector is nothing but 1 1. So here eigenvalue is nothing but lambda equal to 3, which has eigenvector -1 and 1. Eigenvalue lambda equal to 1, we have eigenvector 1 and 1. So as previously what we get from the set of equations, that is nothing but orange one and the blue one, that gives the expansion of the scaling factors. We can get we scale the blue vectors and we can achieve to the target 0 3. But here we get two different vectors. That one is nothing but -1 and 1. Second one vector is nothing but 1 and 1. So now the black one, here it gives the black one. So this -1 and 1, that gives this vector, and 1 and 1, this gives this vector. And note that these two vectors are perpendicular vector. As previously, whenever we consider the blue one and orange one, this is not a perpendicular vector, but from that we can achieve the result. But here it is a general vector that can be achieved at every point of this space. So that's why this is a general vector that can consider as the eigenvector that can be achieved any point on a space with certain magnifications. So this gives the solution of the problem. Crammer's rule, everyone knows that we are not focusing towards the detail of that. So this can be converted into the augmented matrix. We can find out the delta with the delta is nothing but we just keeping the constant term non-homogeneous term away, and we can get the delta. Similarly, delta 1 we can calculate. Similarly, we can calculate delta 2. For x is equal to nothing but delta 1 upon delta x. It is nothing but 3 by 3 equal to 1. Y is equal to delta 2 by delta x is equal to 6 by 3 is equal to 2. This gives the solution of the system of equations. Now, there is a two different form, means we always perform a row operation in a matrix, on a matrix. So equivalent form and row reduced equivalent form, reduced row equivalent form is a major tools to solve any system of equations. So here we have a system 2x plus y minus z equal to 8, minus 3x minus y plus 2z equal to minus 11, minus 2x plus y is equal to 2z equal to minus 3. That can be converted into the augmented form. And using the operations, we are converting this augmented matrix in the form of upper triangular matrix. And all lower terms below the diagonal terms are 0. Then we can consider this particular form is called re-equivalent form. Reduce re-equivalent form. So again, we can extend the equivalent form, and we are strictly convert to the diagonal matrix, has a value 1 1 1, and all the other values are 0. Then we can consider this particular form is called reduced row equivalent form. So now we jump to the application of system of linear equation. So here we are considered as a certain applications that are related with the traffic flow, electrical network, and balancing the chemical reactions. So we start with begin with the traffic flow applications. So here there is a network of roads, and it is of one-way traffic, one-way rules. So it follows the one-way rules. So here the arrow represents the direction of the way actually it can be traveled. So the problem is to find the flow rate of cars on each segment of a street. Here this is nothing but segment of street can be represented with arrows, and there are 4 junctions A, B, C, D are there. So we just name that it has a 4 junction, and there are nothing but the segmented roads are there, in which we can find out the traffic or number of cars passes through that particular regions. So we are just going with the concise with the data. So there are two entry points and two exit points. So this one is an entry point, this again an entry point, this and this are the exit point, and the information at certain points are given. So at that particular entry points, 85 cars enter into the system, 120 cars per hour that can be exit from the system. Okay, let's just this is a 70 cars per hour that can passes through C to D. "45 cars per hour that can passes through D to B, and the rest of the information is not given." So now our target is to the rest of the path. We can find out how many cars passes per hour. So this one is, whenever we does not have any information, we just consider it is a variable x1, x2, x3, x4, and x5. Now, we just observation that the flow into the particular whole system, the flow into the intersection is equal to flow out of that intersection. Means here there is an intersection point is A, B, C, and D. So all that, it is a junction point. So whenever certain cars come from the certain areas, definitely it can be diverted to the other places. So at junction point, we can get certain informations, and we can balance this information at what inflow and outflow. So second thing is nothing but total inflow in the system, that is equal to total outflow of the system. So here there is a two point that enter the cars into the system, and 2 points at which the cars leave from the system. So we just go with in and out. So in here there is a 2 point. One is this 85 cars that enter into the system. X4, there's no information given, so we consider as X4 cars enter into the system. Similarly, 120 cars that can be leaves from the system, and X5 cars leaves from the system. So this becomes 85 plus X4 is equal to 120 plus X5. Now, other information that gives at the junction points. So for at point A, 85 cars that enter into point A, and X1 and X2 are cars that are leaves from that particular point. At point B, X1 cars enter in the system, X3 enter into the B, 45 cars and reaches to the B, and 120 cars that leaves from B. At C, that is X2 cars enter into the C, X4 cars that enters into C, and 70 cars that leaves from C, and X3 that leaves from C. D is a junction point D. So 70 cars that enters and 45 cars exit, and 40 X5 cars exit from the system. So we are just converting into the equations form. So this X4 plus X5 equal to 35. Second thing, nothing but X1 plus X2 equal to 85. The third one is nothing but X1 plus X3 plus is equal to 75. Next one is nothing but X2 minus X3 plus X4 equal to 70. And the last one is nothing but X5 equal to 25. So now this is a system of equations that can be converted into the matrix form, and it look like this way. Now we just converting to row echelon form that we already go through. So this can be defined, that can be gives the information as this particular columns is X1, this column gives X2, this column gives X3, X4, X5, and constant. So this one X1 plus X3 is equal to 75. That gives X1 equal to 75 minus X3. That gives, second one gives X2 minus X3 equal to 10. So this gives X2 equal to 10 plus X3. The next one is nothing but X4 equal to 60. Next one gives X5 equal to 25. And there is one row that gives 0. Means here we have 5 variables. In one, it is a dependent variables. So we can take X3 is free. Any value of we can take, we can consider. That's why I consider as x3 is a free variable. So that gives the solution of that. Means 75 minus x3, 10 plus x3. This one, x3 is a free variable, so we are not allocating any value over here. x5, okay, x5 is 25 and x4 is 60. So that gives the what the allocation of the traffic over the network. Next application that we are just covering here is a electrical network. So here a typical network can be considered, and in that particular sense we can consider that this is a two circuit. One is above upper one, other is lower one. It has a two junction A and B. There are the resistance are there. This is what the battery or capacitors are there. Now whenever we just go with the network, it has a flow of current. So the current is the flow rate of the electric change. So it can be traveled from one place to another place. The electrons are traveled from one place to another place. So here we have two junctions and three types of, means from here it can be start to here, that is the I1 current. It's a junction, so it travel from A to B, that is I3, and from B to A it is I2. Why we are considering this one? Because current flow from negative to positive. So this one, the voltage is negative over here, that can be traveled to positive. Here it is negative, here we can positive. So that can be defined. This particular things is defined to how it can be traveled in the network. So goal is to compute the I1, I2, I3 in this particular circuit. Now we have certain physical laws. On the basis of that we can convert this particular electric network to the what mathematical form. So we use a Kirchhoff law for that. The flow into the junction, here junction is A and B, so flow into the junction is nothing but flow out of the junction. So now whenever we consider the point A, so I1 current is enter into the system at A, and similarly I2 is also enter to A, and the leave is how much leave? It's I3 can be leave. So this consider that I1 plus I2 equal to I3. For at junction B, that is nothing but I3 that enters, and I1 and I2 can leave this particular format. So at junction A, it is I1 plus I2 plus I3 equal I1 plus I2 equal to I3, and at junction B, I3 is equal to I1 plus I2. And we know that from Ohm's law, voltage drop across the resistance is IR. Means here, whenever the resistance comes into the picture, the voltage drop at the form of what? Voltage into the resistance. Current into resistance. The Kirchhoff law, second law, says that in any loop, voltage gain minus voltage drop equal to 0 in a closed loop. So for upper loop, here we consider as upper loop. So here we can start with this particular negative to positive. We can start from here. So it is a what? 15. It's a voltage that gained by the capacitor, that is 15. From resistance it can be dropped. That's why it considered as a minus. So minus 2 I1, because it has a what? Current I1 passes through what? This particular circuit. So this is I1. So 2 I1 minus 4 I3, because here there is a nothing but current I3 is there. So 4 I3 minus, and this is 5 I1, and that becomes close. So this is equal to 0. So here we are using the what? The Kirchhoff second law of mode. For lower loop, here we can start from here. So it is about 20. Sorry, it is 20 minus 4 I3 minus I2, that is equal to 0. So now we have three equations now. One is for what? The circuit, whole circuit, and second one is nothing but the individual loop. So I1 plus I2 equal to I3. Second one is nothing but 15 minus 2i minus 4i3 minus 5i equal to 0. Next one is nothing but 20 minus 4i3 minus 2i2 equal to 0. So that gives in the form of matrix, it is nothing but 1, 1, minus 1, 0. The second one is nothing but 7, 0, 4, 15. Next one is nothing but 0, 2, 4, and 20. So first one is related with I1, second one is related with I2, third one is related with the I3, and this is the constant forms. Now we can convert into the reduced row equivalent form using the row operation. It gives 0.2, 3.2, and 3.4. Means I1 is 0.2, I2 is 3.2, and I3 is nothing but 3.4. So this way we can get the current at every circuit. Now next, we are just balancing the chemical reaction. That's the next application we have. We have a chemical reaction. It is C3H8 plus O2 that converts into the CO2 plus H2O. So our target is to balance these equations. So we just here from first equation, here are the three molecules of carbon, but here we have only one. So we can have a challenge to what the balance the equations. So we just convert into we just multiply with the constant sub variables x1, x2, x3, and x4. Here we are not use the half of the molecules, so that's why we consider that all x1, x2, x3, and x4 are the positive integers. The number of atoms of each element on the left hand side is the same as the number of atoms on the right hand side. Means here we have 3 carbon molecules. Definitely right hand side we have 3 carbon molecules. Here we have 2 oxygen molecules. Here we have 2 and 3. So it must be a balance. So our target is to achieve the balance equation. So here it makes of the 3 different molecules: carbon, hydrogen, and oxygen. So here we can just carbon. Here we have 3 molecules of x1, means 3 molecules of carbon. We multiply with x1. Here we have from right hand side only 1 carbon with x3. So this is x3. Hydrogen, 8 molecules. So 8x1. Nothing. Here we have 2 molecules of hydrogen with x4. Oxygen, here we have x2. Here we have 2x3 plus x4. So this is what we want to find out the value of x1, x2, x3, and x4, so that this chemical reaction becomes what? Balance. So from this we can get the balance equations: 3x1 equal to x3, 8x1 equal to 2x4, 2x2 is equal to 2x3 plus x4. That gives, okay, so when we are considered that x1, x2, x3, x4 all are 0, so it's a trivial solution. It does not make any sense for that. So we can just go through the other solution of that particular form. So we convert into the matrix form, we convert into the reduced row equivalent form, and get the value. X1 is equal to 1 by 4, x2 equal to 5 by 4, x3 equal to 3 by 4, and x4, it does not make value, so it becomes 4. But we know that all the variables is a positive integer only. So here we are considered that x4 equal to 4, then that solves our problems. So we are considered x4 equal to 4. That implies, it means whole system we consider as a multiplicative 4. Then it gives a solution of the balanced chemical reactions. So x1 equal to 1, x2 equal to 5, x3 equal to 3, and x4 equal to 4. That gives the what? Balanced chemical reactions. So the solution ultimately is nothing but C3H8 plus 5O2, that gives 3CO2 plus 4H2O. Now, there are certain terminology that are very hard to understand in linear algebra. So here we are not discussing about the definition, but how it can be defined or how it can be look like. That is a major points of that. So we are just going with a basis vector. Here the vector can be defined as a order pair of 3, 2, and it has an origin. So now this one here. So let's 3 2. What is a 3 actually? 3 is a nothing but it is in x direction, 2 is in y direction. So this is nothing but unit normal vector. It is I in x direction. Unit normal vector is in j direction. Whenever we consider as 3i, so we can expand this I to what? The 3 numbers. This is nothing but the scaling of 3 numbers. It is minus j, means it is a scaling, it is in y direction, it is of scaling of -2, and the resultant vector we get this one. But we are just going with what? This is nothing but, this particular vector is nothing but 3i minus 2j, and here what we consider basis vector. So here we are considering that I and j are the what? Perpendicular vector that can be generated by this vector. This is called what? The basis vector. So this is a base vector. This base vector we can generate any form of vectors, any vector. So this is what? The primary forms of vectors which can be helpful to generate any other vector in that particular space. This is called a basic vector, basis vector. Now, suppose here generally we are just dealing with the what? The two basis vector. It is a perpendicular, and always we are consider this one as a coordinate axis. But now suppose we have two different basis vector and it is not on axis, so what happens? So we are just going with this is a one vector, and this one is another vector. Okay, this is one vector, this one is other vector. So now whenever, can we consider this one is a basis vector? So yes, we are consider this one as a basis vector, and this basis vector is nothing but we can extending and shrinking. We are scaling these vectors and we can get the what? Other vector from these two vectors. Other vector from these two vectors. So we can just scale it and we can achieve any other vectors. But okay, so now this is a one vector actually that we are getting from this one. Now this particular has a value -0.8 and 1.3. Okay, now we are just consider as a standard basis is nothing but this one. This is 3.1 and a -2.1, 2.9. So here basis vector are different. First one we are considered as any vector as a basis vector, and just take this particular point. So it gives a -0.80 and 1.30. It's a x as respect to scaling as respect to the first vector and coordinate, and scaling with respect to the second coordinates. And then after we are considered as a what? The standard basis vector, that is nothing but I and j. Their scaling is 3.1 and -2.9. So the same value that can be defined with the what? Two different basis vector has a what? Two different bases actually. So whenever we change the basis, definitely the value of that particular point has a what? Two different values. If we change the values, then the vector becomes change. So linear combination. So linear combination is nothing but from these two vectors, how many other vectors can be generated that can be considered as a what? Linear combination. So here there's a two vectors a and b. From that we are just changing the scaling factors a and b. We can change we can get the what? Other vector of the what? This space. So this consider as a what? The linear combination of two vectors. So why we are saying that it is linear? Because we fix one vector and we change the other vector. We fix the one vector and we change the other vector, means it gives a line. So first vector is fixed and second vector is moving, then definitely we get a line. That's why it is called linear combination. So linear means one vector fix, change the other vector, that gives line. Change fix second vector, change first vector, then it gives a line. So that gives a linear one. So that's why we are considered as it is a linear combination. If we change the both, we can get the different vectors. Now, a span. The span of two vectors, v bar and w bar, is a set of all the linear combinations that consider as nothing but a v bar plus b w bar. It's a b is a constant, it is not a vector. So a and b are vary over all the real numbers. We can get the all possible vector in the space. Means we can change the value of a and b such that we can get the different point in the space. So how many points? That's the set of all points that are generated by what v and w with the different real numbers. So that gives a span. Definitely, whenever we consider as a 2D, then it covers the what entire plane. And when we go with 3D, that it covers what entire space. So it is 2D and 3D. So we are just going with whenever two vectors are there, definitely it generates a plane. And whenever we are considered as a three vector, they generate the what space. But suppose if two vectors are linearly dependent, then what happens? Means it is a collinear. We already says that it is a dependent, means it is a collinear. So what happens whenever we just go with, then we change the scaling of that, what happens? So this generates a what? A line. So two vectors that are linearly dependent, they generates a line. And whenever we just go with the 3 dimension, and where we are just generating the 3 dimension of two vectors in the 3 dimension, means one vector keeping fixed, then it generates the what? Plane. Instead of what it generates a space, it generates the plane. So whenever two dependent vectors are there, they generate the what? The plane. If it is not dependent, then they generate the space. So dependency reduce the what? The dimension. So vector added the other dimension in the span. Means whenever we add the another independent vectors, definitely their dimension is increased. Now, linear transformation. A transformation is a function, first of all. So we are not worried about the transformation. It's a linear function. So what is a linear function? So it's nothing but whenever we put something input in, that gives output. If you put the values or numbers, definitely it gives the values and numbers. And here we are just discussing about the vector. So we are just putting the vector, it gives the output as a vector. So this is a linear transformation. So how it can be look like this one? So linear. So whenever we just get the input as a vector, that gives the output as a vector. So it can be transformed from one place to another place whenever we apply the what? Transformation or function. So it is what? Whenever we just transform one point to another point, it is not affected to the single vectors. It affected to all other vectors that are associated within that particular plane. So transformation or function that can be affected to the what? Each and every vector in that particular space. So this is nothing but it can be transformed from one place to another place according to the what? Transformation or according to the function. And ultimately what happens? It is not transform only vectors, it transforms the what? The points also. So this is called linear transformation. But types of transformation, there are so many types of transformation are there, but not all are linear. So we just go the video of that. There are certain transformations that can be stretched that can be expand, that can be rotate, oh, it is somehow complicated transformations are there. So this is nothing but the real space that can be transformed to the another space. So there are nothing but there are so many transformations are there. But here we are just thinking about the linear transformation. A linear transformation is nothing but, so just to visualize the form of linear transformation. So this is nothing but stretching of the plane in certain directions. So can it be a linear transformation? So yes, we are just showing, just giving the things is, this is line remains line, means this is a line. After transformation, there is a no curve, means it becomes a line. So then it becomes a linear. Other thing is nothing but the origin is fixed. Origin remains fixed. If change the origin, it does not make the what linear transformation. So like look this way. So this is not a linear transformation. This one, it's changed the origin. It is not a linear transformation. Okay. Can it be go through it's a linear transformation? Can it be considered as a linear transformation? Because their origin is not changed, the line becomes line. So what happens? So this is not a linear transformation, because whenever we trace a line, the resultant line is not a line, it is a curve. So that's why it is not a linear transformation. So there is certain additional things that we have to include. That additional things is the grid line remains parallel every space. Means every space the grid line is a parallel. If the line is not parallel, means which apply the transformation and grid line is not parallel and equidistance, we cannot say that it is a linear transformation. So equidistance is a part of the what? The transformation. It's a line remains line, origin becomes origin, green line remain parallel and evenly spaced. Means the space never be changed. So we can say that such transformation is called linear transformation. So we just go with the properties of that. All line remains line, all origin must remain origin, all lines are parallel and equally spaced. We can say that this particular transformation is called linear transformation. Now, we are just going with the transformation. So here we are using the Gram-Schmidt process. Whenever we have a two vector, why we are just going with the Gram-Schmidt process? It is an orthogonalization process, because whenever we have a two vector and we can apply the transformation over that, it does not get the guarantee to solution of the whole problem. For solution of a whole problems, we require the orthogonal vectors of that particular forms. So we get the solution over the entire space. Definitely we require space or plane. We require what the orthogonal vectors of that particular vectors. So for that, we have to construct the orthogonal vector from the given vector. So for that, we just apply the Gram-Schmidt process to convert any vectors to get the orthogonal vectors. So here we are just giving the particular graphical forms of Gram-Schmidt process that gives the transformation. So here we have three vectors, v1, v2 and v3, that are not orthogonals. They have not in a perpendicular one. So whenever we have considered as a two vectors, so we just projection of v2 over v1 and just direction is opposite to that gives a perpendicular vector of v1 to v2. And the second one, we can get the other vector, we add the other vectors which has the same process. v3 is perpendicular to u1. We can get the projection of v3 over u1, and we get the reverse direction of that, and we can achieve the perpendicular vector, perpendicular properties of v1 and u1. Similarly, we can get the projection from u2 and v3 can be represented, can be considered using the same process. So the Gram-Schmidt process is required to get the other possible solution of the given problem in that particular space. So here, this is nothing but we are just ending our session to that particular information. So thank you. Hello. Hello.
Yes, sir.
Hello.
A second. Yes, sir. A second.
Second.
Yes, Kaushal, sir, thank you very much. It was a very wonderful session. Just a minute, sir. Let me give you the highlights of this session. Sir started with difference between function and equation. Then he covered difference between linear and non-linear equations. Then how to find the solution of linear equations. Then he discussed fundamental elements of LA, that is linear algebra. Then he showed us the methods to solve system of linear equations. Then some practical examples were followed by it, and they were good examples of application to traffic flow, electrical network, balancing chemical reactions, and then the overview of linear combination and linear transformation. So it was really a wonderful session. What I can just say is, Sir brought us to light about linear algebra and its applications. It was an Aflatun session, and I would like to tell you, the viewers, that many courses are there in Coursera, 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 in which linear application is the base, right? So students as well as the faculties should go for these courses. The international certificate is provided there. And moreover, linear algebra is the base of machine learning, which is the current topic, and neural network, in which backend calculations are based on linear algebra. So I would like to thank Kaushal sir that he joined us. He spared time for us. And thank you to RNGPIT family, the trustees and principal Dr. Latesh Chaudhary sir, the coordinator Milind Kansara sir, and entire team who were helping us in making this session very successful. Thank you very much, Kaushal sir. We would like to see you again in another session on another topic. So extending the invitation to see you soon on another topic. So please accept our invitation in advance, sir.
Thank you, Nikunj sir. Thank you.
Okay, over to Milind sir.
Okay. Thank you very much, Kaushal sir.
Thank you, sir.